So section 4.1, it's about vector space and subspaces. We kind of did, part of it in our last class. So part 1, we did it, and part 2, we're going to do today. So let us quickly review what we did in our last class. In our last class, we defined the vector space. And so according to the definition, vector space is a, it's a mathematical structure whose objects are obviously vectors, and then which satisfy those 10 conditions, 10 axioms, okay, 10 rules. And then every time to test those 10 conditions is too much work. And then we decided to test only the 3 conditions, and later we found that any space that satisfy those 3 conditions will automatically satisfy all the other 10 conditions. And that's why we came with the definition of vector subspace. Okay, and vector subspace means it's a vector space from some bigger vector space which satisfy those 3 conditions. And what are those 3 conditions? Condition number 1 is zero vector is there in the space. Second condition, close under addition, and third condition, close under scalar multiplication. So let us quickly review this with this example. Here, let H be the set of all upper triangular 2 by 2 matrix. Is H a subspace of M 2 by 2? Why or why not? Okay, that's the question. Now, one thing to remember is that zero matrix is, if we have, remember the upper triangular matrix is this, let's say A, B, this is the upper triangular matrix. Okay, how do we know that? Well, by definition, we talked in chapter 2. Look at the diagonal, main diagonal, and anything below 0, all the component, all the element below the main diagonal are 0, we call it upper triangular. Okay, upper triangle. We don't care what is there in the diagonal or above the diagonal. We don't care. We just look at the, the values, the numbers below the main diagonal. If it is 0, we call it upper triangular. And let's say if we have 0, 0, 0, 0, then look at that. This one is a diagonal, and below that diagonal is 0. So it is also upper triangular. Above, we don't care, whatever is there. So therefore, keep in mind that 0 matrix is a lower triangular, upper triangular, as well as diagonal matrix. All right. Now, we need to test those 3 conditions, okay? Check 3 conditions. You can do it by yourself. I'm going to do it here, but you try it on your own, okay? 0 matrix is, because it is 2 by 2, 0, 0, 0, 0. This is clearly in H. This belongs to H because is an upper triangular matrix. Upper triangular. Okay, so remember, H is a container. Okay, H is a space, and what kind of objects this space has? All the upper triangular. And 0 matrix in case of 2 by 2 is 0, 0, 0, 0, and clearly this is upper triangular, so it must be in H. Now condition 2, it's a 0. First is 0. Second, let's look at close under addition, whether it is close under addition or not. Let us check that. Okay, for this, let us consider two. Remember how we do this is we consider two vectors. All right, so let us say that A, which is A, B, C, 0D, and B, okay, two vectors, which is E, F, 0, H, for example. We have these two vectors which belongs to H because they are upper triangular. Okay, H is a container and all of its objects are upper triangular. Any upper triangular 2 by 2 matrix is in H. Remember, this one is our vector space M2 by 2 because this is a bigger space. Okay, M2 by 2 include upper triangular, lower triangular, diagonal, non-diagonal, every 2 by 2 matrix is there. So H is, a chunk, a part of M2 by 2. Okay, so this belongs to H. Now we need to show that A plus B, if A plus B belongs to H or not. Let us check that. A plus B will be AB 0D plus EF 0H. This will be A plus E, B plus F, and 0 and D plus H. This belongs to H because this one is a upper triangular matrix clearly. Okay, look at the diagonal, and below the diagonal it's 0 means it's upper triangular. Okay, now condition 3, let us look at that. Close under scalar multiplication. Under scalar multiplication. So in this case, we consider one scalar and one vector. Remember, in this case, our vector is 2 by 2 upper triangular matrix. Okay. Now we are defining vector in a much more broader way, like I said in my last class. Okay, even the matrix is a vector in our case now because it satisfies all those 10 conditions. Okay, let A equals A, B, C, 0D is in H, and let C be a scalar. Let's say K be a scalar. Okay, then what we can write is Ka will be KAB 0D, which means Ka KB 0 KD, and this belongs to H because this is a upper triangular matrix. Okay, this also checks, so it checks all those 3 conditions. So H is a subspace of, since H satisfies all the 3 conditions, I'll write axioms. Since it satisfies all the 3 axioms, H is a subspace of M2 by 2 matrix. All right, that's how we can show. Okay, now let's look at example 8. I think you can do this by yourself, but again, let's try it just for fun, okay? So we need to test, we need to check 3 conditions. Let's check the first one, 0 vector. I'll write here 0 vector here as well. Okay, 0 vector. Whether 0 vector is there or not, let us check that. See here, given h equals, you know, this h can be written as you can see, this can be written as, h can be written as x and x plus 1. Okay, x is real. That's the case. Now, 0 means zero can be written as 0, 0. Can you get 0, 0 from this one? Is that possible? That's my question. Okay, as we have seen, this one, there is x and x plus 1. No matter what value you choose for x, it is not going to be 0, 0. Therefore, this does not belong to, is not in H. Okay, this is not in H. Because for x equal to 0, I think you understand what I mean, right? So no matter what value I choose for x, if I choose x equal to 0, then you'll not get 0, 0. If I choose x equal to minus 1, you get the second component 0, but the first component will not be 0, so you cannot get this. So this cannot be in H. Therefore, so you don't have to test the other two. Okay, so failed. It failed condition 1. Hence, H is not a subspace of R2. All right. Now, sometimes, using theorem makes life so much easy. Here is one theorem, theorem 1. If V1, V2, all the way up to Bp are in a vector space V, then span of V sub 1, V sub 2, all the way up to V sub P is a subspace of V. Recall the meaning of span. What is the meaning of a span? Okay. In chapter 1, we discussed that in great detail. So as the term linear combination refers to any sum of scalar multiple of vectors, and span of V sub 1, V sub 2, all the way up to V sub P denotes the set of all vectors that can be written as linear combination of V1, V2, all the way up to Bp. For example, suppose you have, let's say, y equals, let's say, a1 v1 plus a2 v2 plus all the way up to an vn, then we can write this as, y can be written as a span of v1 v2 all the way up to vn. Okay, so span means linear combination, so generation. So we can create this vector y using different combination of these given vectors. So that's what we call this representation we call linear combination. And then we can write this linear combination as a span. Okay, remember the meaning here. All right, so the theorem tells us that if v1 v2 all the way up to bp are in a vector space V, then span of v1 all the way up to bp is a subspace of V. Now let's look at example 9. Given v1, v2 in a vector space V, and let H is the span of V1 and V2 so that H is a subspace of V. Okay, let's see. Remember, V1 and V2 are the vectors in V. So given V1, V2 in V, and H is given to be span of V1 and V2. So remember, if it is a span of V1 and span of some vectors, then this is automatically a subspace. So by theorem 1, so you don't have to do anything. H is a span of this. So by theorem 1, H is a subspace of V. Done. Alternatively, you can show that we can show that H satisfies 3 conditions. And what are those 3 conditions? Number 1 is zero vector. Number 2, closed under vector addition. And number 3, closed under vector multiplication. All right, so you can show this, you can do this way too. Consider the object from H, because H is a span of this. Means suppose, let's say 0 can be written as 0 V1 plus 0 V2, because now this 0 is actually generated by using this vector V1 and V2. In the same manner, you can show that part, this second condition and third condition by yourself. Either you do this, use the theorem directly, or you can use this. I will call it method 2. Okay, this one is maybe method 1, and this is your method 2. Okay, I leave it to you guys. So just in the same manner as we did earlier, you can show it easily, and if you need help, then just look at my lecture note and I'll provide all the detailed solution there. Okay, I leave it to you. Yes, so number 3 is closed under scalar multiplication, not vector multiplication. I was checking how many of you are paying attention. Thank you. Closed under scalar multiplication. So and let's move forward. Example 10. Okay, example 10. Let W be the set of all vectors of the form where B and C are arbitrary, so that W is a subspace of R3. So clearly, any vector of this form, okay, it has three rows and 1 column. Okay, it is in this form. Clearly, this form belongs to R3. So this belongs to R3. Now we need to show that this is a vector space. I mean, W is a subspace of R3. So what is given here is W is given to be 2B plus 3C maybe let me write this way. Let me write this way. Let us suppose that X belongs to W. Okay, W is a subspace and I want to consider one of the vectors from that subspace. Let us say X is in W. Then X can be written as 2A plus 3B, no, not 3B, 3C, and minus 5B and 2C. Okay, so we can write this way. Now, you can show that W satisfy all those three conditions, but using the theorem 1 that we have just seen, if W is a span of the vectors, then this will be automatically a subspace. I think that makes life a lot easier. So I can write this as, guys, tell me what we can write here is that 2A, oh, that's not 2A, sorry, 2B, I copied the wrong thing. This is 2B plus 3C. So what I can do this is, I can write this as B, and then I'll have 2 minus 5, 0, plus C, I'll have 3, 0, and 2. So I can write this way. So that means if I suppose that this is my vector v1 and this is my v2, then I can write this as bv1 plus cv2. Okay, see, this is a linear combination of v1 and v2. So I can write this as a span of v1 and v2. Right? Okay. So by theorem, maybe you can simply write W here. Instead of X, you can write W if you like, no problem. Maybe that one is even better. So W is given in that form. So what we prove is that W is a, so we have W is a span of V1 and V2. And remember, this V1 belongs to R3 and V2 belongs to R3. Both belongs to R3. Okay, look at the question here. V1 and V2 both belong to R3, and then the W is created or generated by using those two vectors V1 and V2. So hence what we can say is W is a subspace of R3 by theorem 1. It's that easy. You just prove that it is a span of some vectors. And notice that these vectors belongs to R3, therefore W is also a subspace of R3. Now let's look at example 10 quickly, and I think we'll be done with this section. Let H be the set of all vectors of the form is H subspace of R3. I want you to try this on your own, guys. Okay, this part A can be done by both method. Like I said earlier, you can test those three conditions like zero vector, another is vector addition, closed under vector addition, another is closed under scalar multiplication. That's one way of checking whether the given space is a vector space or subspace for that matter or not. And next method, next technique is using the theorem 1. And I think in this case, it doesn't matter which method you use. And I'm using this theorem 1 method, okay? As we can see, I can write this as A and 100 plus B 0, 1, 0, and which is actually the span of these two vectors. If I suppose this vector to be v1 and this vector to be v2, then I can write this as a span of v1 and v2. So if it is a span of v1 and v2, therefore this is a vector space. Yes. H is a subspace of R3. Now let's look at part B. Part B, there is a condition given. A can never be negative. Okay, there is a restriction. In example A, in this one, there is no restriction. You can suppose A and B, anything that you like. But now there is a restriction. Okay, it has to be non-negative. So it will satisfy the zero condition. Okay, you can get all the zeros by supposing A equal to 0, B equal to 0, C equal to 0. And addition, vector addition, closed under vector addition also satisfies. But if you look at this scalar multiplication, it is not closed under scalar multiplication. Make sense? Suppose k, and k is, let's say, -1, for example. If I do that, I'm gonna get this one will change into negative A, negative B, and negative C. See that this negative A must be non-negative. Now, this is not closed under scalar multiplication. This does not belong to H because A is not non-negative. So it does not belong to H. So it is not a vector subspace. Okay. In this kind of problem, you don't have to prove all of these. You just think in your mind and just write what is the reason why you think it is not a vector space. Now I'll write this way. It is not a vector space, I mean subspace for that matter, because it is not closed under scalar multiplication. Scalar multiplication. All right. How about part C? Not a subspace because there is no zero vector. And let's look at part D. So part D, what is given here is that H has all the element of this type A, B, C, where A plus B, 2B minus C equal to 0. So can I write this as, let's say A equals 2B minus 2B plus C. I can write that, right? So that means this guy will become, A can be written as, you can think, again, for this part D, you can so that it satisfies all of those three conditions or it violates one of the three conditions. But the easier method would be using the theorem 1. So maybe what you can do is the easiest way is to write A as negative 2B plus C. As you can see, the condition is given there. I'll write negative 2B plus C there, B and C, which can be written as B, which is negative 2, 1, 0, plus C, which is 1, 0, 1. And if I suppose this to be V1 and this one to be V2, then I can write this as BV1 plus BCV2, which can be written as a span of V1 and V2. So by theorem 1, so H is a subspace of R3 by theorem 1. Okay, done. I leave this part E to you. I think you can do this by yourself without any difficulty, and this section 4.1 is done.